Developed at 1qubit, and we are based in Vancouver. And this work was done with two more people of our team, Arman and Priya. Sorry about the last names. I've been working with them for a year, but still don't get the last names. So basically our work is related to, we want to use a method of classification. To classify graph, we use a similarity measurement. And this is calculated using the weight theorem. So this is my outline. I will start just giving you the motivation of this work. And then I will be defining some basic concept about graph. And then I will go directly to the implementation of the mathematical problem that we are solving on the way. This point, the benchmark is very recent, so we are still in that state, so their results are very preliminary. And we will finish with some conclusions. So the motivation of our work is in the field of the drug discovery process. So basically, when a company wants to put a drug in the market, they need to make sure that the drug has owns certain properties. So one of the properties that we are going to look at here is called mutagenicity. Basically, if compounds have this property, they have the potential of produce cancer. So it's a very important or crucial study to detect this potential property in molecules. So people normally do experiments, but with time they became very expensive to do. So now they are looking at virtual screening. So they are collecting a big amount of data so they can predict this property just by simulations. So how do we do that? Basically, we look at one of the principles in biochemistry, which tell us that when two compounds are similar, their 3D structure is similar, they may have the same property. So for this case, we need to define accurate similarity between molecules, or in general between the representation that in our case is a graph. So before telling you our approach, I will explain, I will take you to the related work. So I just selected 3 types of works. The first one is the most popular one. It's based on molecular fingerprints. So in this case, people represent molecules via vectors of zeros and ones. So basically, this vector has the features of molecules. So if the molecule has the feature, they put a 1. If it doesn't have it, they put a 0. And then the similarity is calculated. They use a distance metric. They just calculate, they use a Euclidean distance or any other type of measure, cosine distance. They are very effective computationally. They are fast. However, they lost a lot of information of the molecules because they reduce this problem to a vector. Then we have the traditional methods of using heuristic, but these are just approximations. So the advantage is that they can preserve the original structure of the graph, so they don't lose information. But they have problems with accuracy. The last related work is very interesting. In this case, they also use graph representation of the compounds, but they look at the specific structures and they use a specific type of graph. And in that case, they can solve the problem efficiently, but it is reduced to those type of graphs. So if you want to go to a more complicated type of graph, their method doesn't work, and then they need to use some approximations too. So our task, our goal will be to develop a metric of similarity and use this metric of similarity to predict the property of a molecule or of a compound. So that's the classification task that we are going to develop. So now I will explain a little bit the problem, and I will go through the traditional path just to get a bit of introduction, and then I will explain what we are actually doing. So normally, a molecule is very easy to be represented as a graph where the vertices are the atoms and the edges represent the bonds. That's very difficult. You can also write the properties of these molecules in the labels of the graph or the labels of the vertices of the edges too. So then the traditional path will tell you that if you want to calculate a similarity between two graphs, you can find the maximum common subgraph between the two molecules. And this is done, I guess you are all familiar with the definition of a common subgraph. A common subgraph is just basically a subgraph which is common to the two original graphs that you are comparing, basically. After that, we require to have a metric, and the most common metric, which is based on the maximum common subgraph, they take the size of this maximum common subgraph over the maximum of the size of the original graph. You can change this definition too, but this is one of the most common ones. So in order to do to find a maximum common subgraph, people build a third graph from the two original ones that you are working on. So you may develop a product graph or a conflict graph, depending on what you are interested in. I just selected the conflict graph in this case. I think that this option gives you a better metric of similarity, because it's not only telling you how similar they are, but they are also telling you how different these graphs are. So basically, a conflict graph has a vertices coming from these original two graphs. So if two nodes are matching, you add a node to the conflict graph. The conditions for matching in an atom, from a molecule, you can look at the atomic number. You can look at that they have the same number of hydrogen bonds, or they have the same order. When you write an edge between two nodes in the conflict graph, you are looking for these similarities in the original two graphs. So if you have an edge in one of the graphs and that edge is missing in the other graph, that is raises a conflict. So you draw an edge between those two nodes in the conflict graph. So basically, in this example, we have two molecules. They are small molecules. However, when you write the conflict graph, you end up having a graph of 133 nodes for this example. And according to the method that we are using, this graph is too big to fit on the wave. So we came up with preprocessing to reduce the size of this graph. I will explain later why this is too big for the wave. So what we do in this case, we take advantage of the structure of the graph. So we compress these cycles of nodes, and these 6 atoms becomes just one node. And then we do the same with every cycle in a molecule. So we keep the information of the original atom. So because we need to recover this metric after we have computed the similarity. So in this case, we go from a graph of size 21 to a graph of size 8. So what we keep here, the labels for the nodes they can be either rings or they can be atoms, single atoms, but we also add the labels for the properties such as like atomic number or the hydrogen bonds. And for the edges, we need to make a difference between edges connecting rings and edges just connecting single atoms. So we put this difference in the labels of this graph. So now we need to build a conflict graph for this type of graph that has been reduced. So you can do two things here. You can compare every single node, but in chemistry, you basically, these molecules are better if you compare same structures. So the function of a ring is not the same as the function of a single atom. So basically, you want to match rings with rings and atoms with atoms. This is specific for this application. If you have any other type of application, that's not necessary to do. But in this case, that's the most logical thing to do. So that's what we are matching here. And the edges is similar to the previous example that we showed. We just add another condition of dissimilarity, which corresponds to the type of connection, which is different when you are connecting two rings or when you are connecting an atom, a single atom. So with this reduction, we go from a graph of 133 nodes to a graph of 12 nodes, which is very good for our application. So the idea will be now, the next step is to calculate a maximum common subgraph between, in this conflict graph. This is not to be equivalent to calculate the maximum independence set in this conflict graph. So this problem is known to be NP-hard, calculating the maximum independence set problem. But in our application and in many other biological applications, finding the maximum independence set is very restrictive. In some cases, you don't want to find the exact match. You just want to find something that is similar. So we want to apply a relaxation to this definition. We want to find a quasi-maximum independence set, to call it somehow. So to explain how we do this, first I just want to introduce some concepts. A perfect grid has certain properties of when you are looking at a dense subgraph. So basically you would like to find familiarity, reachability, and robustness. So the first point talks about that each vertex has many neighbors and only few strangers in that group. The second property deals with the distance between these nodes. So the communication between them is very fast. They are very tied together. And the robustness talk about the connectivity. So if you remove one of these nodes, it's still a very tight group. So many models have been developed to relax these conditions. Just put a list. I haven't gone through all of them, but if you want to relax a familiarity condition, you actually go to relaxations of the degrees of the nodes. These other ones are for the distance, or you can relax robustness, or you can relax density. So in our case, we are interested in familiarity. So the problem that we are going to implement is called K-plex. A definition of a K-plex is for every vertex in this subgraph, we are going to ask to have a degree at least S minus K. So this is known to be an NP-hard problem for any integer K. So in this example of a graph, we can find that when you have K equal 1, you recover the classical K. In the case of having K equal 2, you are relaxing already the condition, and now your graph became bigger. So every time that you increase the value of k, you are increasing the relaxation. So meaning your graph is going to be bigger. So the similarity measurement is going to be bigger too. So as the cliques have the other version of their maximum independent set, oh sorry, that's the triplex. K-plex have also this dual of co-K-plex. So a co-K-plex is the degree of every vertex in this subgraph. It's at most k minus 1. So in this example of a triplex, we can see that the co-K-plex in the complement graph correspond to the figure on the left. So in our case, we are not going to look at for the maximum independent set, but we are going to be looking at the co-K-plex in this conflict graph, which will give us a metric, a similarity metric, which is more relaxed than actually looking for the maximum independent set. So how we are looking for this metric, I need a score. Maybe some people would like to see the actual subgraph that they are obtaining, but for our application, we need to write down a score. And because of the reduction method that we use, this formula is like the most suitable for us to use, so we need to find a new metric of similarity for this quasi-maximum independent set. So instead of using equality methods, we try to define our similarity in terms of subset relations. So if I am comparing two graphs, G1 and G2, I want to see if a subgraph G1 prime or subgraph G2 prime. I want to see what's the rate between the subgraph G1 over the G2 and vice versa, G2 over G1. So for that reason, we define an alpha parameter and a beta parameter, where we use the size of these co-K-plex. So if you notice, A and beta, for alpha we use B1, and for beta we use B2. This is specific for our problem because of the type of reduction that we have made. The reduction implies to repeat some atoms. So you may end up having two different co-K-plex graphs if you are just looking at the graph 1 or just looking at the graph 2. In some cases, you may have the same one, so you just repeat it, but in the case when they are different, you just put it in this format. And then we use a similar technique that the other definitions. So if we put together the minimum of alpha and beta for this parameter equal 1, we will be recovering the other definition of the clique. To be complete, we include the other part because we also want to look at how the other graph is a subset of the other one. So this leads us to a similarity measure. So the mathematical formulation that we use to write this co-K-plex on the wave, we can see it in this equation. So these xi are the vertices in this graph. So 0 if they are not in the co-K-plex, and 1 if they are there. And what we penalize are these extra conflicts in the graph. So we do it until k plus 1. So you can notice that for k equal 1, for the co-1plex, we are recovering the maximum independent set, and our equation is already is in a cubal form. For higher order, let's say for k bigger than 1, we have a higher order polynomial. And in that case, we need to do some hobo to cubo. And this will increase the size of the number of variables that we need. So in the problem that I mentioned before of 133 variables, if I want to use that one for a 2-plex or a co-2-plex, that will increase my, in the worst case, will increase to 133 square, which is like too big for the weight. So a size 12 is nice. It's very nice on the weight. So this is the complexity that the worst case that you can find for this type of problem. So the benchmark that we are using in here uses a classification, a classifier. We just selected this simple classifier, the k nearest neighbors. So this one uses a distance measure, which in our case would be 1 minus the similarity metric that we already defined. And the parameters that we need to optimize for these classifiers are the k, which is the number of neighbors that you want to consider, and phi, which is the distance parameter that we have in this similarity metric. And in all our simulations, we use k equal to for the whole k-plex. So we're only solving whole 2-plex. So basically, we want to predict the property of the molecule by majority voting, and we also use some weight voting. So the data set that we are using is available on this website, and it's big. And in that paper, they say that that's the biggest one that they have so far. For issues here, it has like 7,000 plus compounds, and they are all with like very well known, like the property, the mutagenesis property. That's still a very big data set for us. We started selecting a subset of these compounds. So these results are very preliminary. We are still running some data. So the first thing that we selected was like just 320 molecules, just to see what happened and to prove our method. So what we found so far is that the error rate is not that good. It's 41%. But this is actually a very small data set compared to what these people are doing with 7,000. So it's a little bit optimistic. So if we can improve our technique or improve the classifier that increase the data set, that we may end up having a good accuracy too. So this was a very short talk. And we can compute that we have developed a measure of similarity in which we are comparing graph using a conflict graph and using this technique of a maximum co-k-plex. This co-k-plex optimization has been mapped into QVOT and implemented on D-Wave. The importance of this optimization problem is that it has many more applications, not just for graph similarity, but for other type of real-world applications. And then the other thing that we have done is that we have implemented an effective graph reduction of this problem, so it can be suitable for the weight. And well, if we are hoping for the next for the next device that we can implement more molecules or bigger molecules, or maybe this technique won't be necessary. Well, so far we are working on a bigger data set, so to have a more accurate benchmarking, and we would like to extend these techniques to other applications or methods. So thank you very much.
Questions?
Any question?
What's the question?
Get a rough idea of what sort of traditional method have achieved in terms of error rate on the data set you consider?
Yeah, the people that Yeah, the most common method is the molecular fingerprints. The data that we got here in that paper, they get like an accuracy of like 87%. So is very high. It's very high. So one of the things that we have to do is just to take the same methods and compare with the data that we have by using the same method. That's still work in progress.
Any other question?